Hi folks, welcome to section 12.3, Trig Equations and Identities. This is where we take all the groundwork that we laid in the last couple of videos and we put it to work in some kind of problem-solving situations and some sort of more complicated equations. So the first situation we're going to look at is equations that extend beyond 2 pi. So for the last few equations that we've done, we've had domains like this. We've looked from 0 to 2 pi, which makes sense. That's the first positive revolution. But of course, you can have answers that go beyond 2 pi. And graphically, going beyond 2 pi just means that you start the graph sort of over again. It repeats itself because trig graphs are periodic graphs. So if I were to think about the graph of cosine that says let's solve cos theta equals negative a half from 0 to 4 pi. Let's think about that. Cosine would be a graph that looks like this. It starts here at 1, and it goes top, middle, bottom, middle, top. There's one cycle of the graph. Okay, and that would get us to 2 pi. But if we wanted to go to 4 pi, we'd just repeat the same thing again, because it's a periodic graph. So we'd actually get 2 cycles of the graph. And if we wanted to solve the equation, well, where does that equal, say, negative a half? That would be all the intersections that we'd run into here. And you can see that we're actually going to have 4 answers. Now, we can do this on a graphing calculator, and maybe we should take the time right away to solve this graphically, because if you had your GDC, that's what you'd want to do. So if I want to solve this graphically, I'll put in the graph of cos x and also the graph of y equals negative 0.5. I'll head to my windows and make sure that I'm going from 0 to 4 pi. That really is 4 pi, but I'll type it in again. 4 pi, enter. So about 12.56. And my y's are going from negative 1 to 1 because the graph goes down to a min of negative 1 and up to a max of 1. Let's hit graph. And you can see that there are intersections here, and here, and here, and here. And we could use our GDC to find those intersections. So I'll go second calc, intersect, and for mine it's a touch different than for yours. I got to choose a left bound and a right bound. And it'll tell me that there's one at 2.09. That's what it says in purple. Okay, and I can repeat that, and I'll find some other ones. I'll get a left bound right here, and a right bound, and I get another one at 4.19. Okay, and there are 2 others at 8.38 and 10.47. So in approximate terms, I mean, those are our solutions. 2.09, 4.19, 8.38, and 10.47. But there's something fishy here. This solution right here and this solution right here, they're kind of the same looking ones on the graph. They should be 1 period apart from each other. And cosine is a function that happens periodically. It's got a period of 2 pi units. So these should be 2 pi apart. If I found this one and added on 2 pi, I'd be at this one over here. That's why they're about 6.28 apart. There's a little bit of rounding difference here. Same thing if I chose this point right here in yellow. It's going to be a periodic buddy with this one. So if I add 2 pi to that first one, 4.19, I'm going to end up at this one. If we're doing this in the GDC, well, we just sort of plug and chug and find those points of intersection. If we want to do it analytically, which we do, here's what we're going to do. We're going to do our regular stuff. We're going to figure out what the reference angle is. So where is cosine a half? Oh my gosh, that happens at 60 degrees or pi over 3. And you'll have a point that says a half root 3 over 2. We've been using this 60 degrees a lot. The reference angle is root 3 over 2. What quadrants might we be in? Well, cosine is going to be positive in quadrants 1 and 4. It's negative back here and here. Okay. So That's going to give us two fairly straightforward solutions. We're going to have this first one that looks like this. Now that would be pi, but take away pi over 3. So the first one, pi minus pi over 3. The other one that I see there is going to be pi plus pi over 3. Okay? And in both these cases, we just go to a common denominator, and we can find our sort of reduced version. So 2 pi over 3 and 4 pi over 3. And guess what? Those are the exact values of these first two that we found over here, 2.09 and 4.19. So there are answers at 2 pi over 3 and 4 pi over 3. And they're also going to have periodic buddies that recur 2 pi later. So let's think about that. If I took 2 pi over 3 and I added on a cycle, which would be 2 pi, or 6 pi over 3, I'd be at 8 pi over 3, which I bet you dollars to donuts is 8.38. Okay, that's going to get us here. And if I took this one and added on 2 pi, let's think about that. That would be 4 pi over 3 plus 2 pi. So just one cycle later. Graphically, it just means going from here over to here. Well, I'd have to think of that 2 pi as 6 pi over 3, and I'd get 10 pi over 3. 10 pi over 3. Okay. So that's our fourth solution. And those are the exact values for what we found approximately. So essentially what we can do is we can find the solutions that are in the first cycle and then just add on periods until we've exhausted our domain. If I added another 2 pi, well, that would get me beyond the far boundary of 4 pi. And if I went in the negative direction, like back here, I would be at negative angles, and I'm only allowed to go, according to this domain, from 0 to 4 pi. So there are our four solutions. In that first one, the period was 2 pi because the graph hadn't been messed with. It was just cosine of theta. If there's a coefficient beside the angle, the period of the corresponding function has been changed. And so when domains are strange or there's an operation on the angle, here's essentially what you should do. And this is what we just did. Find the solutions that are in the first cycle of the graph. So essentially find this one and this one. Okay? And then add, subtract periods until you exhaust the domain. So in this one, we added 2 pi's because the period of cosine is 2 pi. Now in this next one we have over here, the period is not necessarily 2 pi. So the period of cos 2 theta, remember we have this little equation because we've seen these graphs before. That's why we did this chapter in this order. The period is going to be 2 pi over what we were calling the b value, or the coefficient here. So 2 pi over 2, or just pi. That means whatever solutions we find are just going to recur every pi units. Let's think of it graphically. If you had cos of 2 theta, okay, if I graphed this function, I know that it's going to do this. It's going to go up, down, middle. Okay. That's going to get us to pi because the period of this function is pi. So I guess to get us to 2 pi, we'd have another cycle of the graph. But wait, we could also go backwards. Down, bottom, middle, up. That would get us a cycle in the backwards direction. Get us to negative pi. Oh my gosh, but we can go all the way back to negative 2 pi. So that means we're going to have even another cycle. Gosh, I really hope that this is a GDC question because that would make it a lot easier. But there's essentially the function over that domain. And what we're asking is, where is it at negative 1/2? So essentially, where are all those intersections? And you can see there are going to be 8 solutions. I'm suggesting that you should find these first 2 solutions and then just add on pi or subtract off some pi's until you found all the rest of them. Okay, let's go through that process analytically. So it's going to be the same sort of thing to start off with. The reference angle, we've already established cosine is a half at 60 degrees, or pi over 3. And we know that cosine is going to be negative in these 2 quadrants. We've actually already done the grunt work of figuring out that one of those is going to be 2 pi over 3. And the other one is going to be 4 pi over 3. We just did that in the very last example. One thing that is different here is that the whole angle is 2 theta. So instead of saying theta equals 2 pi over 3, we're going to have to say 2 theta is 2 pi over 3, and 2 theta is 4 pi over 3. In this way, our little sketch of the angles that we just made, it helps us get to the answer, but it actually doesn't represent the answer in the end. So it helps us get to this stage right here. And now for each of these, if I want theta on its own, I'm going to have to divide by 2. So 2 pi over 3 divided by 2 would be 1 pi over 3. And 4 pi over 3 divided by 2 would be half of 4 is 2, so 2 pi over 3. This gets us our first cycle answers. Okay? So because we had a 2 theta, we had to do that extra step of division by 2. So the full solution set is going to have that pi over 3 in it, and that 2 pi over 3. Okay? I can say x is the set of all these things. And then those solutions are just going to recur every pi units. So if I add pi onto pi over 3, I'll be at 4 pi over 3. And you might say, hold on, that was already an answer from before. Yeah, but this is a coinky-dink that we've got the same answer happening. If I add pi onto this one, where will I be? 2 pi over 3. Again, we can go into dreamland and figure this out. 2 pi over 3 plus pi. That's plus 3 pi over 3. Hey-yo, that's 5 pi over 3. Which is getting very close to our boundary of 2 pi. Right? 2 pi would be 6 pi over 3. So if you were to add on yet another cycle, like if you took this 4 pi over 3 and you added on another pi, you'd end up at 7 pi over 3, which is too far. Okay, so that's beyond our boundary of 2 pi, so let's just get rid of it. The thing is, we can also go in the opposite direction. We can take away some pi's from these. So I could take this 2 pi over 3 and I could subtract off a pi. That would mean that I'd go from this one right here, and I'd be trying to find where its buddy periodic solution is back here. So 2 pi over 3 minus a pi. Okay, so that's going to be minus 3 pi over 3. That's negative pi over 3. Okay. And same for this one. We could go and subtract off pi from that. So that would be like 1 pi over 3 minus 3 pi over 3. Haha, that's negative 2 pi over 3. And the IB is not going to ask you one with this many solutions. We just want to go through the process that you can just keep going until you're out of domain. So I can take this one and, sorry, I actually need to put it on pen mode. This one, and subtract off another pi. Negative pi over 3 minus pi. So that would be going from this one here and trying to figure out where its periodic buddy is back here. Minus pi, again, I'll think of that as 3 pi over 3. Hey, yo, I get negative 4 pi over 3. And I'm kind of, I should have made myself a little more room. I'll put that brace bracket in again in a second. And this one, I'm going to subtract off pi again. So that'll be negative 2 pi over 3 minus 3 pi over 3, or negative 5 pi over 3. There are 8 solutions, and that doesn't really surprise us from the graph that we drew or from the graph that we could have drawn with our GDC. Okay. You don't have to write the brace brackets, but I just want to make the point here that we're talking about sort of initial solutions here in blue, periodic buddies that were 1 period forward, periodic buddies from the initial solution that were 1 period backwards, and periodic solutions that were really 2 periods backwards from the blue one or 1 from the green. Okay. So we add or subtract periods until we exhaust the domain. That's kind of tricky, so let's do another one. In this case, we have a tangent equation. I'm going to do it as if we actually remember the properties of tangent. So the period of tangent is always pi over b instead of 2 pi. Now, I hate this one. It says x over 3. So I'm just going to think in my head that means tangent of 1/3 x. So the b would be 1/3. So pi divided by 1/3, which would be pi times 3 over 1, or a period of 3 pi. So whatever answers I find, they're going to recur every 3 pi units. I'm going to do part of this with some insight about tan, and part of it maybe forgetting some of the nitpickier things. I want to make the point that it can be pretty elegant if you remember all the tan properties, but if you forget them, you're still okay. And I'll show you what that means. So the reference angle, where's there a tangent of 1? That'll happen at 45 degrees or at pi over 4 from our unit circle. And that's because we're at the point root 2 over 2, root 2 over 2. Y over x would just give you 1. So tangent's 1 at 45 degrees or pi over 4. Okay? And we're talking about a tangent that is negative. So it could be in this quadrant or this quadrant. Tangent's positive in the first and third. So let's figure this out. So that means there are my reference angles. And I'm wondering, okay, what is this angle? So this angle would be pi minus pi over 4. It's less than 180 degrees. And we could think about that. Okay, that means 4 pi over 4 minus 1 pi over 4 makes 3 pi over 4. That's on our way to the answer. Okay, the other thing that we can figure out is the other possible answer here. And some people at this point are saying, hold on, can I get away with less work? Yes, you can. So this is a little less than 360 degrees. It'd be 2 pi minus pi over 4 or 7 pi over 4. Okay, I'm going to erase some stuff here that was just scrap work. And I'm going to say to myself, all right, it's not just x that equals that, it's x over 3. So x over 3 equals each of these, because the angle is not just x. So if I want x on its own, I need to times both sides by 3. So that'll give me x equals 9 pi over 4, and x equals 21 pi over 4. Those are both numbers that are between 0 and 10 pi, because 10 pi would be 40 pi over 4. Okay, that's the boundary. So we can write the answers. I can put my nice brace brackets here. There are no negative ones, so 9 pi over 4 is the lowest. And we got 21 pi over 4. And we can just add on those 3 pi's. Okay, so I can take the 9 pi over 4 and add on 3 pi. And this is where it gets kind of sneaky or elegant, depending on your sort of definition. So 9 pi over 4 plus 3 pi. 3 pi is the same as 12 pi over 4, just making a common denominator. Oh my gosh. That gets us this 21 pi over 4. We actually already had that answer. And the reason for that is that tangent recurs more frequently than sine or cosine. The default period is pi or 180. So if you find just the first solution for a tangent, then you can just use the period to find all the other solutions rather than having to find the first two. But it's okay to have found both of those first solutions, both of the ones in the first revolution or the first cycle, you might think of it. It's just a little bit redundant. Okay? So from there, we can just keep going. We can say, all right, well, I'll find the next answer. That would just be from here. I'm going to add on 3 pi. Okay, so let's think about that. 21 pi over 4 plus 3 pi. Again, 3 pi is 12 over 4. 3 bucks is literally 12 quarters. So that's going to give us 33 pi over 4. There's another answer. Okay. And if I added on another 3 pi, let's try that, plus 3 pi, it would give me 45 pi over 4, which is too far. Okay, it's beyond 10 pi because 45 over 4 is bigger than 10. So let's get rid of that. It's really just these first 3 solutions. Okay. And because it's a tan, it all sort of came from the first one, but it's okay to find those first 2. Also, if you find the first 2 and you botch the period and say it's 6 pi, you'll be safe. Okay? Even though it's not true for tangent. Tangent has a slightly different period. If you find those first 2 solutions, things will work out for you. So, in these questions where we want to find the solutions in the first cycle, we might have to watch out for operations on the angle, so that we might have a little extra step. And then afterwards, we're going to add and subtract periods until we're all out of domain. There are some questions in your book on page 520, and I'll get you to do number 1 and 2 ABC. If you want to do D as a challenge, that's great too. Good luck with the material, folks, and take care.